All right, ladies and gentlemen, the purpose of this lecture is to understand the relationship that exists between wavelength, frequency, and energy carried by electromagnetic waves. Something you have seen recently in our discussions of atomic theory is that there is a fundamental relationship that exists between light and matter. And in particular, we looked from our historical atomic theory discussion to the idea proposed by Niels Bohr that in fact the energy levels of electrons are quantized. That is, they're only allowed in specific energy level positions within the atom. And transitions between those energy levels lead to the production of photons of light. And those photons of light have a characteristic in that they are both particles and at the same time they exhibit wave-like characteristics. So to have a complete understanding of matter, we need to have an understanding of the interaction between matter and light. And that's what the lecture for today is all about. So we'll go ahead and begin here by talking about some of the characteristics of waves. Much of this information will be review for those of you who have had physics last year. But to start off, the waves that we're going to be most interested in are light waves. And light waves, as it turns out, are a type of transverse wave. That is a wave which carries energy perpendicular to the direction that it travels. And another type of wave that is also a transverse wave, kind of a good analogy to think about here, are waves within the ocean. Those waves travel horizontally along the surface of the ocean, but the direction of the energy carried by those waves is up and down. That is, if you're sitting in the ocean, the wave will move you kind of bobbing up and down in the water, increasing your potential energy as you move upwards there. Light waves are very, very similar. A light wave is a transverse wave that exists as an oscillation within an electromagnetic field. And to describe the properties of these transverse waves, the first thing we want to look at is the separation between two adjacent troughs or crests of a wave. That separation of the adjacent troughs or crests is referred to as the wavelength of that particular wave, and we symbolize it in our equations with the Greek letter lambda. So wavelength is given generally in units of meters. For visible light, where those wavelengths can be very, 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 very small, typically we'll measure those visible light in wavelengths of nanometers, recalling from our discussions of prefixes that nano is a prefix which refers to a billion, and therefore there are a billion nanometers in 1 meter. So we've got a wavelength, the distance between adjacent crests or troughs. Another property we can use to describe waves is their frequency. You can imagine if you are standing along the edge of the ocean and just counting how often those waves pass by you as they travel. The frequency would be defined as the number of waves that pass by within a given unit of time. Generally, it is given in units of waves per second, or really just inverse seconds, which is a unit we refer to in physics of a hertz. So we've got the wavelength of the wave, the distance between adjacent crests or troughs. We have the frequency, that is the number of waves that pass by per given unit of time. And the third property we measure about these waves is the energy carried by those waves. From your physics days, many of you recall that we define energy as the capacity to do work. Typically, we measure energy in units of joules, or for larger quantities of energy, we might measure it in units of kilojoules. And it seems logical for us to understand that, in fact, waves do carry with them energy. As we discussed, those water waves can lift you up and down, changing your potential energy, thereby doing work on you. Light waves, also, we know can carry with them energy because we understand that ultraviolet radiation from the sun, which is really just a particular frequency of light wave, carries with it energy that can cause you sunburn. Infrared radiation can transfer heat to things. So we understand here that not just water waves, but also light waves carry with them energy. And the next portion of our discussion right here, what we want to focus in on is the relationship that exists between these three variables, that is wavelength, frequency, and energy. And we have a couple of equations that describe the relationships between these variables. The first thing to recognize here, guys, is that if you multiply the product of a frequency, which we use that Greek letter nu to represent, times a wavelength. A quick analysis of the units here will kind of lead us to an understanding of what this product of these two values actually represents. Frequency is measured in units of hertz or inverse seconds, and we said wavelength could be measured in units of meters, which implies multiplying frequency by wavelengths gives us units of meters per second, which is a unit of speed. So the speed at which a wave travels is the product of its wavelength times its frequency. Now, one of the things that's kind of odd about light waves is that regardless of their wavelength or frequency, they all travel at the same speed. And that speed of light in a vacuum is approximately equal to a value of 3.00 times 10 to the 8th meters per second, or 300 million meters per second. So very, very fast. As it turns out, the fastest that something can possibly go. And in our equations, we're going to give that speed of light the variable c, because in fact, the speed of light is a constant. That is, it does not change as long as you're traveling through the same medium. And given that the speed of light is a constant at 3.00 times 10 to the 8th meters per second, that implies a particular relationship between frequency and wavelength. That is to say, if the frequency increases, in order to keep the product of frequency times wavelength constant, that would imply the wavelength would have to decrease. That is to say that there's an inverse relationship that exists between those two variables. The higher the frequency, the shorter the wavelength. The longer the wavelength, the lower the frequency. Which implies, therefore, if you know one of those two variables about a particular photon of light, that is its wavelength or its frequency, you can calculate the other by using the equation that we just developed for speed. That is, the speed of light is equal to the product of wavelength times frequency. Now, the second relationship that exists between these variables is a relationship between energy and frequency. And it kind of makes logical sense as an analogy here to imagine that if you're sitting there bobbing up and down in the ocean, the energy carried by those ocean waves is going to change depending upon how frequently those ocean waves move past you. That is, if the ocean waves are moving past you more frequently, they can lift you up into the air more frequently and thereby do more work upon you, which implies the frequency of that wave is proportional to the energy which it carries. And as it turns out, that direct proportional relationship that exists between energy and frequency is described through what we call Planck's equation. That is, energy is equivalent to a particular constant. We call that constant Planck's constant. It gets the variable h, which has a value of 6.626 times 10 to the negative 34 joule seconds, multiplied by the frequency. That is to say, again, there's a direct relationship between frequency and energy. If frequency goes up, the energy carried by that wave goes up as well. Now, something that can be useful to save yourselves a little bit of time as you're looking at these equations is to recognize that between the two equations, we have a common variable that is frequency. And because we have a common variable, that means we can make a quick substitution here that will allow us to calculate energies without having to stop by and calculate frequency first if we know the wavelength. Recognizing that the speed of light is equal to the product of frequency times the wavelength, I'm going to go ahead and rearrange this equation to solve for frequency by dividing both sides of the equation by the wavelength. And when I do that, this cancels out over here. I get that the frequency of light is equal to the speed of light divided by its wavelength. And now I'm going to take that expression for frequency and plug it in to Planck's equation. And when we do that, we get a new expression here, which is that energy is equal to Planck's constant times the frequency, which is really equal to the speed of light divided by the wavelength. And thereby we get a new version of Planck's equation defined in terms of wavelength rather than in terms of frequency. So together, these three equations here, that is, the speed of light is the product of wavelength times frequency, energy is equal to Planck's constant times the frequency, or energy is equal to Planck's constant times the speed of light divided by the wavelength. Those three variables can allow us to interchangeably make calculations involving wave behavior. Let's take a look at a quick example problem to see how those calculations might play out. So for an example, let's say that we're looking at some red light that has a wavelength of 700 nanometers. And we want to go through and make a calculation of the frequency of that light and the energy carried by a photon of that light. So first things first, given that we have a wavelength in nanometers, let's go ahead and make a quick conversion from nanometers into meters so that our units will end up agreeing here. So we're going to go ahead and make a quick conversion. Monorail. Recognizing that nano is a prefix which means 1 billionth, that implies that there are a billion, or 10 to the 9 nanometers in 1 meter, which gives us a wavelength of 7 times 10 to the negative 7th meters. And next, we're going to go ahead and solve for our frequency of light from our equation for the speed of light being equal to the wavelength times the frequency. I can rearrange this equation to solve for frequency by dividing both sides by the wavelength. And when I do that, we end up with a new expression here. That is, frequency is equal to the speed of light divided by the wavelength. Because the speed of light is a constant, I can go ahead and just plug in the value of that constant into our equation, that being 3.00 times 10 to the 8th meters per second. We can divide that by our wavelength, which we just calculated in use of meters here, of 7 times 10 to the negative 7th meters. And making that division right there, this comes out as a value that is equal to, let's see, looks like about 4.29 times 10 to the 14th inverse seconds or hertz. So we've got a pretty high frequency here, even though this is a relatively long wavelength of visible light. And next, we can go ahead and make a calculation of the energy carried by this photon. We could either use our equation defining energy in terms of frequency, or we can go back to the one that we had from our given values, which was energy is equal to Planck's constant times the speed of light divided by the wavelength. Let's go ahead and use that version right here. Plugging in our numbers here, that gives me a number of 6.626 times 10 to the negative 34 joule seconds. That is Planck's constant, we defined for you above, times the speed of light for light, which is 3.00 times 10 to the 8th meters per second, divided by the wavelength of our wave. We want to make sure here we are careful with our units, because we've defined the speed of light in units of meters per second. We want to express the wavelength in meters of 7 times 10 to the negative 7th meters. And as we make this calculation, make sure you watch out for our units here. Taking a look at those units here, we have seconds canceling with 1 over seconds, meters cancels over meters, and that leaves us simply with units of joules, a unit of energy. And this value comes out to be, looks like about 2.84 times 10 to the negative 19th joules. So we got some answers here. Something that's kind of nice to keep in mind as we go through these problems. For visible light, just so you can kind of have ideas about what seems like logical answers as you're going through and solving your homework problems. Visible light has a frequency which is generally on the order of magnitude of 10 to the 14th hertz or so, and an energy per photon which is generally on the order of magnitude of about 10 to the negative 19th joules. So if you're dealing with a problem that deals with visible light, as long as you get answers that are somewhere in this range, that's a good piece of evidence that in fact you've done the math correctly and haven't made a calculation error along the way. So that's how we make some calculations involving wavelength and frequency and energy. We'll go ahead and have a quick move along here to a quick discussion again of that visible light. Recall we just said that the energy carried by these photons of visible light is generally on the order of magnitude of 10 to the negative 19th joules per photon, and the frequency is on the order of magnitude of about 10 to the 14th hertz. Here is a value, a set of wavelengths which correspond to light within the visible portion of the electromagnetic spectrum. Generally, the shorter wavelengths of light should be higher frequencies due to the inverse relationship between wavelength and frequency there. So violet light is the highest frequency of visible light which we can see. That has the short wavelengths on the order of magnitude of about 380 to about 420 nanometers. And then as we move through our rainbow there, we move up to the longer wavelengths there. The longest wavelength of visible light which we can see is red light, which has a wavelength of between about 660 and about 720 nanometers or so. So if you're making calculations, again in meters, recall that on the order of magnitude of meters here, those wavelengths range from about 3.8 times 10 to the negative 7th meters for those short wavelengths of violent light, up to about 7.2 times 10 to the negative 7th meters for the long wavelength red photons of light. And that portion of light that we see there in the part of the visible spectrum is really just a tiny fraction of all the different wavelengths that possibly could be created. That just happens to be the wavelengths of light that our eyes are sensitive to. But there's a whole lot of other types of photons of light that we still can experience in a variety of different ways. And that's what this spectrum is that we have down here on the bottom of this slide. This is a spectrum that gives us kind of general areas of the visible light spectrum in terms of what we call those different particular wavelengths of light. Now, running through here real quick, just kind of to keep things in perspective here, recall we said that the red wavelengths of light were the generally longer wavelengths, and therefore those were the generally lower frequency portions of the visible spectrum. The violet side of that spectrum was the shorter wavelengths, and therefore the higher frequency portion of our spectrum. And because frequency is directly proportional to the energy carried by these waves, that also implies those low frequency wavelengths are also the low energy parts of the spectrum. And the high frequency parts of the spectrum are therefore our high energy portions of the spectrum. So looking at that spectrum here, let's just kind of go through and point out a couple places where you've seen these other types of light here. If we move from the visible spectrum, that is the red end of the visible spectrum, to a lower frequency than red, we move into what we refer to as the infrared portion of that spectrum. We generally experience infrared radiation in the form of heat. You can kind of imagine those heat lamps they sometimes use at restaurants for sitting outside of the patio when it's cold. You notice that those heat lamps produce infrared radiation and kind of spill over into the red portion of that spectrum, so you can see that light. Even lower frequency, longer wavelength than that infrared radiation, we experience that as what we refer to as microwave radiation. And then we move on to the very, very long wavelengths of this light in the television portion of the spectrum and radio waves. Some of those radio waves can have wavelengths into the tens or hundreds or even thousands of meters. Moving in the other direction from the higher frequency portions of our spectrum here, past violet, we see, well, we don't see, but we experience light as ultraviolet radiation, ultra being beyond. So here we are in the higher energy portions of our spectrum, meaning we're moving into positions where these types of light can be dangerous to us. So we have ultraviolet radiation in the violet portion, past the violet portion of the spectrum. Moving up to even higher energy past ultraviolet radiation, we move into the X-ray and gamma ray portion of those spectrums there. Gamma radiation being really just very, very high energy X-rays. And again, we recognize that these are, again, in the dangerous portion of the electromagnetic spectrum, because if you think about your X-ray technician, generally when they take your X-rays to the dentist office, they usually go and hide behind a concrete barrier to protect themselves from those rays. So again, the lower frequency of the visible spectrum tends to be low energy and therefore of relatively little danger to humans. The higher frequency tends to carry with it more energy and therefore can cause significant damage if you absorb it with your body. So there's our electromagnetic spectrum. Last thing we want to talk about, but not least here, guys, is a quick discussion of the relationship that exists between matter and energy. And this is going back to the discussion we had in historical atomic theory about the development of that model of the atom from Niels Bohr, where we determined that the positions the electrons could occupy in terms of potential energy levels within that atom were quantized. That is, there were only specific allowed energy levels that exist in terms of electron positions in the atom. Now, the evidence that we have from that experiment is a lab which you're going to be doing in class, and that is to say that when you look at the light produced via a emission tube, we call them, by exciting electrons up to higher energy states inside of a diffuse gas tube, those electrons, as they move up to higher energy states from their lowest energy or ground state, those electrons move to a higher potential energy position. And just like putting a ball up at a higher potential energy position, that's an unstable position for that electron to be in. it could lose potential energy and thereby become more stable if it were to fall back down to a lower energy state. But the trick is, as a ball moves from a high potential energy to a low potential energy state, that change in energy that it loses as potential energy is gained as kinetic energy. That is, energy is conserved. But when you move an electron to a higher potential energy state, as it falls back down to its lower potential energy, it doesn't gain in kinetic energy. Instead, it actually conserves energy by emitting a photon of energy, that is a photon of light. And the energy carried by that photon of light is directly proportional to the frequency of light which we observe. Now, Bohr had been expecting to see in this experiment an entire rainbow of light produced because he imagined, just like with a soccer ball, you could put that electron at any particular potential energy within the atom. And thereby, as the electrons fell back down, we should be able to produce every single possible value of frequencies of light, every single energy of photon should be produced from that. But what he observed was very, very different. He instead observed only specific frequencies of light, that is, only specific colors of light were produced as those electrons relaxed back down to their lower energy ground state. And from that, he came up with this idea that, in fact, if only specific colors of light were produced, that implied that only specific energy level transitions were allowed for electrons within atoms. And that's where we got this idea for the Bohr model atom, in which we had those electrons existing in this series of concentric shells, or different discrete potential energy levels within the atom. And if you saw a electron move to a high potential energy state and then fall back down, it should emit a photon proportional to the change in potential energy which it experienced as it fell. That is, if we compared two different photons, one of which fell a larger distance and one of which fell only a smaller distance, the photon which fell the smaller distance experienced a smaller change in potential energy. And as it experienced a smaller change in potential energy, because energy is directly proportional to frequency, that should imply that the frequency of that photon should be lower for the photon which only fell the smaller amount of potential energy, which would imply, therefore, due to the inverse relationship between wavelength and frequency, that the photon of light emitted by the electron which only fell one level should be a longer wavelength of light than the wavelength of light emitted by the electron which we've shown here falling from the fourth shell down to its ground state. And that's what you are going to observe in your experiment involving the emission spectra tubes. You're going to be looking for the relationship that exists between wavelength and frequency and correlating that to what we understand about the relatively specific allowed energy levels that exist for electrons present within an atom. And that concludes our discussion of the characteristics of waves. Thanks for listening.